So jumping in 4.2, properties of functions. Remember the last class in 4.1, you learned about how to move functions around, up and down, left and right, or horizontal and vertical. We can stretch them, we can view them, we can compress them, flip them across the x-axis, flip them across the y-axis. It's just how you can kind of, and basically the reason for that is, let's just be honest. You want me to just like be just bare bones and just like transparent. Most of the time, let's be honest, in the real world, are you going to be sitting there and your boss is going to give you some sort of equation? Well, first off, they're probably going to give you an equation. But if you see data modeled, you're going to sit there and go, is this moved over? No, you're going to be using computer programs. They're going to do all this for you. But once again, and I like to stress this a little bit, college algebra is very beneficial to a lot of areas in life, financial math, a lot of areas like that, statistics. Past college algebra, statistics is a breeze. As far as the math side of it, the math is going to be like mind-numbingly easy. Matter of fact, your calculator does all your work for you. But this does help you, for those of you, and like I said, I have students every semester go, I'm never taking calculus. Never going to take it. And I had a student who wanted to be a lawyer, and then all of a sudden he found out the law school he wanted to get into required him to take all the way up to calculus 3. Okay. They said, just for us to even look at you, we want to see math. Okay. So you never know. Whatever career you might have might require some upper level math. So knowing how these things kind of look in a very rudimentary way is going to help you. Now, this right here, properties of functions, and some of the stuff you've actually kind of toyed with a little bit. If you go back in time, whenever I was teaching you how to graph quadratics a semester ago, for those of you who have me, remember I said quadratics were kind of fun to graph because if you found the vertex, you could always find what? One point. And then what was going to happen? You got gifted another point because it was a mirror image of itself. So it's kind of nice. Okay. If you can keep that in mind today, that's going to help out. Okay. Because for some reason, and like I said, you people are a lot smarter than me, and I'm not saying that to be facetious or downgrading. You are. We're going to be learning about even and odd functions today, along with some other things. But for some reason, I never quite got it. I was like, what do they mean by even function? And how do you just know? Until I finally just boiled it down, like, oh, well, duh. Okay, so let's jump right into it. Let me show you what an even function is. Once again, if you can revert back to 3-4 in your head and just remember what the base function looks like, it helps out a lot. It really does. You can go up. Even if you can just give yourself a sketch, you can know if it's an even and odd function. And sometimes it's neither. Okay. But there's a couple ways to check. So let's look at this guy right here. Y-axis symmetry. Y-axis symmetry says the graph of the function f has y-axis symmetry or is symmetric with respect to the y-axis if f of negative x is equal to f of x for all x in the domain of f. Such functions are called even functions. Man, that makes no sense if you're not reading that carefully. Like as a math guy, you have to kind of like stop, slow down, read it carefully. But then notice they give us a formula here, and I'll give you both of them. It says one of them is f of x. That's just our normal function, right? The other one says this. If I replace that x with a negative value and plug it in, it comes back out with the original f of x, which is right here. Okay, now, let me be honest with you. Some of you are going with like, how do I plug in a negative x? Well, that's all you do is you're just plugging it in, right? And then when it comes out the back end here, notice they match. When they match, you have an even function. But you know what I know what's beautiful about if you understand 3-4? Well, can we know that this is a parabola? Well, a parabola says this. Doesn't that just show you that it's an even function because it says it has y-axis symmetry. It's already there. It's already built in for you. There it is. And because you already knew a parabola has y-axis symmetry, okay, or x-axis symmetry if it's laying on its side, okay, you can go, well, of course it's symmetrical because I know that whenever I plug one in here, it comes out here as the same number, okay? Here's how you can always test it if you don't want to plug in x's. Pick a point. Pick any point you want. Like notice on this one, I'm going to give us a very simple function because I don't want to spend all day long just solving something like this. But if I gave you a function just like this, g of x is equal to x squared. We know that's a parabola, right? Well, how about I pick two numbers? Both of them have to be the same because that's why it's saying you can replace x and a negative x. Well, notice if I put g of 2, 2 squared is equal to 4. Well, how do I know it's an even function? Because look, what if I replace it with g of negative 2? Well, negative 2 squared is equal to what? 4. Notice the same number popped out the back end. The exact same number popped out the back end. So therefore, it's an even function. Don't think because I used an even number. It would have worked with 3, 4, 5, whatever. Okay? That lets me know that's an even function. You know what's nice about even functions? Anybody wondering, who cares? You have to start graphing these things. You're getting what I just said. You're getting that 2 for the price of 1. Hey, if I graph 1, I got another one over here. Okay, if I graph another, I got another. So instead of having to graph 2 points, I can graph 4 points. Okay, but I only have to do math for 2. Okay. They're mirror images of each other. Knowing what you know right now, can you think of another even function? Go back to 3, 4 in your head. Go through the Rolodex of pictures you have of graphs. And think of one that looks like, man, it's exactly the same on one side as it is the other. Always good review. About absolute values. Wouldn't absolute value just be a v? That's an even function because what I get over here isn't going to give me the same thing over here. Now I have different x values. I may have a positive 2 over here and a negative 2 over here, but whenever I go up, they're going to be exactly the same. Okay? How about any even exponent? X to the power of 4, x to the power of 8, x to the power of 10. You're just widening out that base a little bit, right? But it's still going to be a mirror image. So therefore, it's an even function. Does that kind of help y'all kind of see them a little bit better? You get into trigonometry. Cosine is an even function. You'd see that later on if you ever take trigonometry. It just means it has y-axis symmetry. Okay? Well, notice you can also have something called an odd function. This one right here, and I'm gonna kind of back it off here just a little bit so I can draw it. This one don't start thinking, okay, odd function, that means it's going across the x-axis. No, it is a mirror image across the origin, okay? Which means you're gonna have something that looks like this, okay? If that was a piece of paper, that would be where you would fold it, like that. And so that's where they become symmetrical at, okay? Notice what happens with this one. Look at the function. My original function is negative 2x cubed plus 8x. Now, the picture I am showing you, okay, is just a base function, is it not? Okay? But now look at what's going to happen. When I replace f of x with a negative x, look what happens to everything. Everything in the function went opposite. Okay? See, because here we had a negative, Here, this is positive. Here we have a positive, and here we now have a negative. Everything flipped. That tells me I have a negative function. Or, once again, do what I said to do earlier. Go in there and replace it with some numbers. Okay, pick one number, make one of them positive, make one of them negative. First off, you should get the same number, just one's going to be positive, one's going to be negative. So let's look at it again. Let's do another test. We have g of x, and we know the base function of this whole function is going to be what? The base. Yeah, x cubed. So notice with x cubed, if I come in here and just put, let's say, g of 2 again. Keep it easy. That means I have 2 cubed, which is going to give me 8. But notice if I put g of negative 2, well, that becomes negative 2 cubed. Well, that thing's going to stay negative, isn't it? But I'm still going to have out the back end, now I have a negative 8. But notice the 8 still showed up. That tells me I have an odd function. So if you're having to graph one of these, you're still, believe it or not, you're still getting 2 for the price of 1, aren't you? Except what's going to happen now? Now you've got to go, hey, when I plug in this number, like if I plug in 2, well, now guess what? Now when I plug in my negative 2, I got to make sure that this guy becomes a negative. Whatever it is going to be the exact opposite. And that's how you know. Now remember, your line of symmetry for this guy is the origin. You would literally be folding that thing over, okay, on the x-axis, and that's how you would get that odd function, how everything kind of works, okay? So we mirror across the origin for odd functions. Now, you can have neither. Okay? You can have a function that is neither even nor odd. Let me tell you what's going to happen. First off, do you kind of understand what they're doing right here with these negative x's? Okay? Because notice, negative x cubed becomes negative x, which is going to make that a negative 2. That's what happened over here, but a negative and a negative make a positive. Negative x here stays, that's going to make that guy a negative. Okay? What's going to happen here, and notice, like I said, this is a complete opposite of what? The original function. The original function had negative 2x cubed plus 8x. But the new one had a positive 2x cubed minus 8. It's an exact opposite. With the even function, you got the same function out the back end. What's going to happen is if you have a neither, it comes out and it's not the same. Like this one would have said, like at the bottom here, if this was a neither function, you'd have had like, say, negative 2x minus 8x. Well, notice that's not the same. And it's not a complete opposite. It's really just some signs have changed. Okay? There wasn't a complete reversal of parities or a matching. So if it doesn't match at all, and it doesn't do one of the things I just said, you have neither. One of those could possibly be a neither would be like a square root. Think about what a graph of a square root looks like. It's just a hump, isn't it? Well, there's no x-axis symmetry there. There's no function on the other side. There's no function across the x-axis. So that would be a neither, because if I plug in something else, I'm not going to get the same thing anymore. Okay, does that kind of help you out a little bit? Notice, like I said, with these, honestly, if you can picture the base graph in your head, it takes a lot of the guesswork out of it. I mean, literally, some of these, I don't even do the math on them. Some of them in your homework, you're going to have to, because they're going to be just weird enough that you're going to go, oh, hey, I must see an x cubed. It's obviously going to be this type of function. But be careful. Sometimes because of the coefficient they're using, it makes it not even. So you got to be real careful about that. Okay? And like I said, if you don't want to be plugging in x's and negative x's, plug in a number. plug in one number that you want to try twice. Like here, usually I pick one, but one or two. I'll pick a one and a negative one and a negative one. If I pick a one, it better look exactly the same on the back end. If it's an even function, right? When I plug in the negative one, it better look exactly the same, no matter what. So, and we got some examples. Some helpful hints. We say that an equation x and y is symmetric with respect to one, and I give you some other little hints here. The y-axis, if replacing x with negative x, results in an equivalent equation. Same function. The x-axis, if y with negative y results in the equivalent equation. What you're seeing there is this one. You don't deal with it a lot. For this one, let's pretend like you had that. Okay, that's for number one. Number two would look like this. Okay. So like this one right here would, if you wrote it back in the day, you would see this y is equal to x squared. This one will be x is equal to y squared. You're just seeing a y squared. Now, mind you, y squared is not a function, but we can still say it has symmetry. Okay. And then the origin, if replacing x with negative x and y with negative y results in an equivalent equation. Literally, it's like your cube root function is one that looks like that. Not cube root, I'm sorry. Well, I don't think cube root's a function, so even have to forget it. And then right here, I give you some more guidelines if you want to download them or whatever. There's some pictures. I won't hang out on these too much. You can download these off your notes and look at them. Good, okay? You okay on that? More or less. Play with it a little bit. Intervals of monotonicity. Monotonicity, sorry. Monotonicity. Okay. What this is saying, you're going to look at a graph. You're going to look at and sometimes they're not going to give you a graph. Sometimes they're just going to give you a function. And you're going to decide if between a certain interval, okay, is it increasing or is it decreasing or is it a constant? Okay. I'm going to read what this says very carefully here for you. Okay. And then I'm going to give you some little hints on how to do it. Because some of your Hawks homework gets a little bit confusing, just a little bit, okay? So I kind of want to clear a little bit of that up. You have an increasing interval. It's getting larger, okay? If for any x1, a point, and x2, in the interval with x1 is less than x2, that means you have to make sure that your one point is smaller than your next point, okay? You can't, this isn't like finding slope where it doesn't matter which way you do them. No, your x1 has to be your smaller point. So if I'm going from like 0 to infinity, I can't use 2 and then 1. I have to go 1 and then 2 or 1 and then 3 or whatever. Okay, I have to do it in that order. Okay, same thing as going negative. I have to use -1 and then have to use -2 and then use -1 because -2 is smaller. Okay, that's what that's saying. It is the case that f of x1 is less of f of x2, which means you have an increasing function. The same thing can be read on decreasing, except now x1 is larger than x2. It's basically saying when you plug in this number and you plug in this next number, the numbers that pop out, you're going to see one's larger, one's smaller. Okay? So let me show you how this looks like. Look at this function here. Determine the intervals of monotonicity. I'm not going to keep saying that word. Okay. And I'm not going to say the word mono either, because then that's just going to get weird for everybody. Okay. Determine the intervals. Okay. And they give us a function. We know the base function is x squared. We should know x minus 2 says it's going to be moving 2 units to the right and 1 down. Okay, that's our transformations that we just learned. Okay. So we know the domain is R. Okay, we don't have any restrictions on anything. Okay, so the domain is R, but now let's do some test points. So notice watch what I'm going to do here. I'm going to pick an x1 and x2. I do know this. The vertex is right here, right? We can all tell that. You all know where the vertex is. It's the lowest point on the graph. We're going to get more in detail on that. You cannot include your vertex. You cannot use it as a point because at that point right there, it would be 0. I mean, technically, I guess you could, but don't. Pick a point off of it, okay? Because technically, at that level, your graph is neither going up or down, right? It's at that perfect level, okay? So I'm going to pick 2 points here. I'm going to have an x1. And my x1, I'm going to pick is going to be 0. My x2, my second point, okay, is going to be 1. Notice my x1 is smaller than my x2, just exactly what it told me to do, right? Do the math, okay? Literally, you plug in everything. So you've got this f of x, so I'm going to have 0 minus 2 squared minus 1. 0 minus 2 is negative 2. Negative 2 squared is 4. 4 minus 1 is 3. Simple enough there, isn't it? And then I'm going to do the same with 1. I'm going to come here, 1 minus 2 squared minus 1. 1 minus 2 is negative 1. Negative 1 squared is 1. 1 minus 1 is 0. Well, look at this. My x1 is larger than my x2, which means the function here, the function of x1 is larger than the function of x2, because we do know that 3 is greater than 0. I can scroll back up here and go, okay, what's happening to the function right there whenever that happens? Look right here. Is it decreasing? Yeah. So look, from this interval from here to here, this guy is going down. He's coming this direction. Or I'm sorry, wrong, other side. From here, he's going down. That function is coming down. I get it. And now I want to demystify something. I get the fact that you're seeing arrows here. Those aren't directional. Those are just saying that line will extend to infinity. There is no directionality in the arrows themselves. The directionality of this thing is coming from what? What you just did. So now you know that this function that we've always talked about coming from infinity and going to infinity, it didn't just appear, it came. It started from infinity this direction, and we don't know what it's doing over here. So let's find out. Let's do it again. We need to find out the other side now. Test points again. I'm going to pick, so let's say I pick 3, and then I'll pick 4. Why am I picking those? Because they're nice, pretty points. Okay? So notice my x1 is going to be the 3. My x2 is going to be the 4. Always making sure my x1 sub 1 and x sub 2, x sub 1 is smaller than my x sub 2. And then we're going to do some math here. We're going to have 3 minus 2 squared minus 1 is equal to, and then we're going to do 4 minus 2 squared minus 1. 3 minus 2 is 1, 1 squared is 1, and then you're just going to get a 0 here. 4 minus 2, 4 minus 2 is 2, 2 squared is what? 4, 4 minus 1 is 3. So notice I've got just opposite numbers here, but the point of the matter is this, is notice 0 is less than 3, which means my x1 is less than my x2, which means my f of x1 is less than my f of x2, which just coming back up here to the top again, looking at our deal, anytime you see that happen, look right here. We know the function here is doing what right here? Yeah. So from the vertex, looking toward our right side, this guy is increasing. From here back, it is decreasing, or sorry, it's decreasing. So this is how you would write it, and this is how it's going to happen in Hawk. We have two squares pop up, and it'll say decreasing on, increasing on, okay? So we are decreasing on what? Now remember, you can't use your test points. This thing, does it not have a line of symmetry? Right there, right? So what is happening from where x equals 2 when we go off to the left? What's happening? It's decreasing. And in actuality, okay, while it's decreasing, and I actually kind of wrote my deals a little wrong here, my arrows. Decreasing means this function is going in that direction. So I kind of want to change these around just a little bit. And I want you to think more in directionality of this way, because it's going to help you with your interval notation a little bit. You think more like this, okay? So what's happening to the function there? Where's it going to go? Where? Yeah, to negative where? Yeah. But where does it quit decreasing?
At -2, 1 negative.
Think of x values. Because you're doing a domain right now.
At 2?
At 2. Can you include 2?
Oh, yes.
No. Because at 2, what's happening at that function? It's dead straight. It's neither decreasing nor increasing at that vertex. So you can't include the 2 at this point, okay? So it's decreasing from 2, okay? And then, so it's increasing where?
From 2 to positive infinity?
Yeah, exactly, 2 to positive infinity. And now you have a idea of what's happening to your function at these points. And the reason I'm getting rid of those arrows, the downs and ups and stuff like that, believe it or not, that is actually getting ahead of myself, because you can't really tell the directionality of the function. I mean, the line itself, okay? That's something you'll learn, once again, if you take higher math. They call parametric equations. It tells you the actual, like, what's happening to that line. Is it going down? Is it coming up? So, but this is saying that function, where's it going? It's going to negative infinity. And I get it. You can kind of tell from the graph, sort of. But don't forget, the math may be telling a different story. The graph says one thing, but the math, for all you know, this thing could be doing something different when you do the math. Good. Okay, so be careful with that. Always do the math to it. But knowing the graph helps. All right. I'm about to say a word, but I want you to think of it this way. Just think vertex. Okay? Local extrema. Okay? The reason why we're going to call it this way now is we're going to get into different types of questions eventually where you're going to start optimizing things a little bit. Okay, so a function has a local maximum at C. If there is an open interval from A to B containing C for which f of x is less than or equal to f of C for all x in A and B. In this case, we say f of C is the local maximum value of f. Okay, I can keep reading that or just show you what this means graphically. Look. There's an open interval from here to here. Okay, so here's my A. Here's my B all the way over here. I've just picked two arbitrary points, A and B. Okay? Somewhere inside there is a C. And that C is the lowest point. Okay? Somewhere inside that interval. Okay? And what that is saying is at that point right there, that f of c, this right here would be called a local, what do you think? Minimum or maximum? Minimum. Same definition over here. F of c is just some point, right? Some point. Whereas over here, and then I picked some arbitrary, like little boundary lines and said, hey, between here and here, there's another extreme. Now, the reason notice they're not showing you a whole function. You're going to see why. Okay? Because some functions do this. They may go up and down for a while. And so I may have to say, hey, from here to here, what's happening? And then from here to here, what's happening? From here to here, what's happening? Okay, so you may have in one function different extrema. You may have in one function, you could have three, a minimum, a maximum, and a minimum. Okay, this one right here is obviously going to be a local maximum, exactly. A lot of the times these are used for like optimization. It's going to be like saying, hey, remember whenever we did some of those maximum problems where it says, hey, let's maximize the profits? That's what you remember, the vertex? That's the same thing. You were taking the vertex of something and going, let's maximize the profits in this area. Let's minimize our losses. Okay. Well, those are for very simple functions, but we can do it for more extreme functions. And we can say, hey, if you're going to do something from here to here, this is what's happening. Okay. Let me show you one. Look at this guy right here. Notice, give you this graph, let me kind of scroll all the way down a little bit here. I only show you step one. I'm going to go ahead and write down step two because I'll be honest, Hawks, the way you have to answer it, it's weird. Okay, so once you answer a couple, you're like, okay, I get what they're doing. But it's just the way they make you answer it. Okay, because the way you have to read them. Okay, so notice we have a function here. Hopefully you can kind of tell, what does this function look like to you? Not completely, but what do you think it is? Probably. How about execute? Doesn't it kind of have that weird shape a little bit? Except it's just a little bit more what? Exaggerated. Instead of just doing this little nice hump, it's got a lower hump and it comes back up. And so this is a function that some stuff has happened inside of it to make it kind of a little bit more skewed at the origin. Okay, and that's fine. But notice what we do have here. Do you see a local minimum? Yeah, right here. I have a local minimum right here. Okay. So there's my minimum. But do I also have a local maximum?
Yeah.
Yeah, right here. Okay. And the reason prior to this, I said, hey, from any open interval from here to here, okay, what it was saying was this. If I have some test points in here, from like say here to here, here's my A, here's my B, look at that right there. From between those points, I have a local minimum. If I come over here and use some other points, say E and F, in between those two arbitrary points, I have a local maximum. Okay, that's what that definition was saying. That's sort of getting the math out of the way. Okay, good news for you guys right now. You're going to be looking at this going, okay, here we go. Now we are going to start finding things like this. There is ways mathematically to always find these. Okay, which once again becomes easier in calculus, ironically. Calculus, you can do all this in your head, man. Okay. Watch what's about to happen. Step one. Okay. Find the local minimum. Okay, well, my local minimum says this. It says use the graph to determine the locations and types of local extrema. Write D and E or does not exist for all extrema that do not exist. Well, think of one that might not exist. If you see a function, straight line. A straight line would not have, right? Where's gonna even a straight line, and where's your local extrema? Doesn't have one, okay? So kind of watch out for that. Or if I pick some arbitrary points in a weird area, like say I said, hey, what if I said, is there a local extrema in those points where that yellow line's at? No, there's no highest point, lowest point, kind of like, there's no point where it's going to start changing and just start decreasing. No. So that's what we're looking at here. We're going to say, okay, Hawks is going to have you answer it this way most of the time. It's going to say, hey, where is your local extrema? Step one. And you're going to have to give the X values first. And then you turn around and give the Y values on step two. Okay. So step one is literally saying, hey, I have a local minimum. At where? Well, when I come over here and look at my graph, don't I have one at -6? Okay. And what is the value at -6? Now here, this is where I'm getting a step further, okay? This is your step two. The local value at 6 is going to be what? So at -6, the value is going to be your y-axis. So it's a coordinate point. -6, -7 is a coordinate point. That's all it's asking for, okay? It's just they're splitting it up into two sections. But we also have a local maximum, don't we? What would be my X value? Exactly. 0. And what is the value at 0? Exactly. The value is -1. Now, mind you, I just did step one and step two inside my step one. Okay. And I'll be honest, when I first did this, I tried to put this in as a coordinate point, and it gave me that stupid thing. It says, you don't need this. And I'm like, ah. And so literally, when that happens, I'm not even gonna lie to you. Because I make sure if I'm doing your homework, I do the practice a lot before I go to certify. I click, show me the solution. What do you want this? How do you want this written down? Oh, okay, I get it now. And then I go back, hit try similar, and then just do a different one. And then make sure I got it right, okay? Make sure I generally understand. Now, is it gonna be that way on your midterm? Probably. But if you gave me a coordinate point, am I gonna be hating on you? No, you saw it. Just make sure to read your graphs carefully. I have a whole intermediate class that filled their last assessment because nobody knows how to read a graph. Okay. Online class, man, they don't have me there teaching them. So they might get a redo. Oops. Are we good on that? Are you good okay with the local extrema? I don't want to skip past stuff. I mean, the math of this, the notes of this, and everything else looks really, really weird. I get it. Because of all the terminology they're using with functions and open intervals and stuff like that. One, I suggest go back and look at my definitions. Learn to read definitions now. Even I have to read this one up here and look at it and have to parse out that information and go, okay, what is it saying and why? And yes, this helps a little bit, right? The picture, okay? But if you can take the picture and then sometimes, it helps plug in numbers, okay? Every single one of my teachers I've had in my master's degree, literally, every single one of them would say, I have to draw a picture. I have to draw a picture. I have to plug in numbers. These guys are geniuses. I'm not a genius. Okay? But when I see what's happening with the numbers, my simple brain goes, I know the difference between a negative number and a positive number. I know which one's larger. Oh, I see what they're saying now. Okay, this is what's happening. Kind of helps you out a little bit. Okay? And then you can go impress people with your intelligence at a party or.
Everyone's favorite party trick,
Exactly.
math problem.
Statistics is fun at a party trick, believe it or not. Like, did you know if you have a room of 99 people, the chances of 2 people having the same birthday is almost 100%?
Oh, that's cool.
You wouldn't think that, would you? Out of all the birthdays, 365 days of the year, but there's a 99% probability that you have anything more than actually 70 people in a room. It gets exponentially larger, so you can make a bet. So I'm gonna blow this up just a little bit here, so you can kind of read a little bit better. Look carefully with this average rate of change. Just lose this. Okay. Alrighty, so average rate of change. Given a function f defined on the interval, notice it's including the endpoints, okay? A and B, where A cannot equal B, the average rate of change of f over those points that you've chosen is f of B minus f of A and B minus A. If y is equal to f of x, then any of the following expressions may be used to represent the average rate of change of f over A to B. Inclusive. Includes the endpoints. Change in f, change in x is equal to the change in y, change in x. Equals, okay, Greek word. You're gonna take statistics, get used to Greek. Use a lot of Greek. This right here, that little symbol, anybody know what that symbol means? Tells you. Read it. Delta. Okay, right. Okay, it means delta. Okay, that is the capital Greek letter, delta. I've been learning Greek lately, so. Okay. There's no C in Greek, so it goes alpha, beta, skip that, it goes delta, gamma. Okay, or gamma, delta, it actually goes G then D, but still, all it means is change. The change in Y over the change in X. Or f of B minus f of A, or B minus A. Hey, you know, you've seen this before. You realize that? Everybody's looking at this like you've never seen this. So look at this carefully. So notice you're just seeing a slope. Okay? Because wouldn't that be the average rate of change? What is a slope? But hey, I go up 2 over 1, up 2 over 1, up 2 over 1. Isn't that not the change between this point to the next point? Okay, that's what you're seeing here. Okay. You pick 2 points. And then you go, on this interval that we are including, how do you know you're including them? Because of the brackets. On these 2 points, I'm going to have a rate of change. Well, what is the rate of change? Well, let's look. They give us a function now. Okay. And then we come in here and go, okay, well, I know this is going to be f of B minus f of A all over B minus A. Correct? And they give me 2 points. Now, hear me out. This is not a coordinate point right here. These are 2 different points on a line. Okay? On what kind of line? Well, it's quadratic. I know it's quadratic. I'm looking at it because there's a power of 2. Okay? So we come in here and literally, to do this not really the long way, okay? But we're going to have to come in here and subtract these functions. Okay? Come in here, and this is how it works. I've got 3 squared minus 5 times 3 plus 2. Right? I just replaced the 3, right? Because isn't that going to be my second point? Because my B, I have to use my second point first. Okay. Technically you do, okay? Technically, remember when dealing with slope, does it really matter which way you go? It's going to be the same slope, right? Okay. If you get negatives, they're just going to cancel out. Okay. But notice I have a minus. My formula calls out a minus, which means, hey, guess what? you better throw up a parenthesis just in case, okay? And then start replacing everything. Three, 1 squared minus 5, 1 plus 2. All over 3 minus 1. I'll leave you to clean that up. Very simple. Use your calculators, right? Okay. When you end up finishing this off, okay, you end up getting this. You get 27 minus 15 plus 2 minus 3 plus 5 minus 2 all over 2, which is going to equal 14 over 2, which is equal to 7. So my average rate of change is 7. Not hard math, right? But could it get messy? Yeah. So be slow, be intentional, take your time. Let's look at one that's a little bit weirder. Okay. Look at this one. Notice they give me 2 different points here. The average rate here, I want you to be very aware of this because once again, definitions matter. Okay. This line right here that I'm drawing, that is called a secant line. Okay. If you've taken geometry anywhere in the past, you could come in here and go, okay, there's a secant line there.
I'm doing the fire inspection, just looking.
No worries. Good. You would still place everything the same way. Okay, so watch what's going to happen here. I've got an A, I've got a B. Let's still replace everything. Don't be afraid of just variables. I know, once again, I get it. Numbers, you're like, I love numbers because they end up simplifying to something pretty. Well, let's look at this one. And I'm gonna work out, I'm gonna do skipping. I'm gonna have to, because of sake of time, I'm gonna have to skip some steps, but I would suggest go in there and learn how to do some of these, like get it cleaned up. Okay. So notice I would come in here and replace it the same way again. Let me pull back down that function so that we can see it. I've got 3x squared minus 5x. 3x squared minus 5x, was it a plus 2? Yes, plus 2. Okay, so notice I have an A and a B. My B is going to end up being 3 C plus H squared minus 5 C plus H plus 2. And then I hit the minus and I put me a big parenthesis again, right? And then I've got 3 times C squared minus 5 times C plus 2. All over, well, C plus H minus C. What's going to happen to those C's on the bottom?
And cancel.
Yeah, these guys cancel out. Clean this up a little bit. Notice that C plus H, what's going to happen there is I'm going to break that guy up, remember? Because you can't distribute that power 2 in there. So let me skip that step, and this is what it's going to look like. When you get him all the way foiled, okay, you end up getting 3C squared plus 6CH plus 3H squared minus 5C minus 5H plus 2 minus 3C squared. Yeah, plus 5C minus 2. That was horrible line. That's better. Look at it carefully. Come in here, notice, hey, I have a 3C squared and I have a negative 3C squared. I have a positive 2, I have a negative 2. negative 5c plus 5c. Look at the rest of it, there's nothing else, right? Nothing else can cancel, so I can rewrite from here. And then notice I have, well, if I put this in order, doesn't really matter, okay? Watch what's about to happen. I have 6ch plus 3h squared minus 5h all over h. You should notice there's an h in every single one of the things on top, so I could factor out an h, which is going to leave me as 6c plus 3h minus 5 all over h. H reduces out. And you're left with just 6c plus 3h minus 5. That would be your average rate of change. Okay. What you just did was called the difference quotient. Remember that? Remember you saw that x minus h before, and then it had f of x minus h minus f of x all over h. Remember that when you did that one before? Same thing. Because what happens in calculus is what we say is this. Hey, what happens if I make h 0? We'll actually call it taking it to a limit. Okay? Well, if h goes to 0, what's going to happen to this 3? It goes away, doesn't it? And so then I'm just left with 6c minus 5. Well, believe it or not, that's just called the derivative. And the derivative is, technically, it's not your average rate of change. It would be your instantaneous rate of change. What's happening right there at that spot? But you just took the average. Okay? But this is the formula. So, and ironically, once again, this ugly, ugly math is done in your head in calculus, because if you want to be truthful about it, here's a little hint. 2 times 3 is what? Yeah. Get rid of the x. Because this part, we don't worry about the h's calculus. So literally, it's literally, we just look at it and go, there it is. I mean, it's literally one of those things you're like, but for you, you've got to do the math. Because right now you're looking for averages. Okay, because you don't have the tools to figure out instantaneous anything. You're looking at averages, average rates of change, average things. Okay. I say this to get you to take calculus. I don't teach calculus. I'd love to teach calculus out here, but we have one lady who's really good at it, and she's taught it for like 20 years. Okay. So now I've taught calculus as an adjunct at other places, but I'm trying to show you that this class is a lot harder than calculus. So if you're sitting here going, man, I don't want to take that. I don't know, why not? It's actually way easier. Way easier than any intermediate class I've ever taken. Okay. I got some more notes on here. I got one more note here, but it literally just shows you, and I'm not going to show you the notes for this, and we're going to jump into the next lesson. But hey, let me give you what would be the, just tell me if it'd be positive, negative, or none. Okay? I'm going to just kind of draw some stuff here. We'll use the highlighter here. If I said the points f of a and f of b, would that be a positive rate of change, negative rate of change, or no rate of average rate of change? Here's my A, right? Here's my B. Yeah, look at what's the lines in. Look where the points are at. They're negative. So that would be a negative. Okay, well, how about from f of b, okay, to f of c? Would that be a positive or a negative? Yeah, because look what's happening to that. Think of slope. What's happening to the slope? Is it a positive slope? Is it a positive line? Or is it a negative line? Okay. You're right, that's a positive. Well, how about f of a to f of c? Yeah, neither. There'd be no, it's a straight line. What happens on a straight line? What's the slope of a straight line? Nothing. Realize what you're seeing here. Why am I showing you this like this? Imagine this. I say this because hopefully you are. You invest some money right here at A. Then a war happens. What happens to your money? Gone down. And then you get so scared, you start seeing it come up. So what do you do at B? Man, I'm going to withdraw because I don't want to lose any more money. But then some people in this room decide to go, man, I'm investing for the long haul. I don't care. Whatever happens between now and 15 years, I'm not investing for right now. So some people get it to here. Now, mind you, this is say after 5 years. Well, notice after 5 years, you're back where? Exactly where you started. But where's that line going? Up. That means if you hung out. Now, what smart people do is this. Now, I do mean smart people. When crap hits the fan, you know what they're doing? When this thing starts to go this direction, you know what they're doing? Ignoring that, we're ignoring that. But they're buying at all these little increments along here.
May I have your attention, please? May I have your attention, please? The fire alarm has been activated in the building. The fire alarm has been activated in the building. Please proceed to the stairways and exit the building. Do not use the elevators.
Only one floor. I think the elevator works. So do you kind of get that though? But notice it's the average age.
May I
Like I
have
said,
your attention,
this is not a
please?
finance class,
May I
but
have your
still, it's good to
attention,
kind of know
please?
these things.
The fire alarm
Okay.
has been activated in the building. The fire alarm has been activated in the building. Please proceed to the stairways and exit the building. Do not use the elevators.
All right. That's 4-2. Are you okay with 4-2? I do have some examples here for you all the way through. I would suggest looking at the example. We're going to get into 4-3, especially one that's kind of tricky, and I did put it on here. Maybe I did. I think it may be this one right there. No, that's an even function. It may be in there. But be careful. Look at them carefully. Okay, work out the math to see what even and odd functions are. Like I said, all of those have been filled in your notes. Okay. Let's jump in. We'll finish up. See we don't get interrupted again. Combining functions. Most of these are actually, believe it or not, super easy. There's one weird part. Okay. Which we might be able to get to today. I hope we can. This has really slowed me down, this fire alarm stuff. 4-3 overall, like I said, overall pretty simple. Just be real careful. Okay. It more gets weird about the math. You're gonna get a lot of blue bars. So do some simplification if it can. Okay. But notice it's just literally saying these things right here. If I have two functions, okay, f and g, then I can do all these things to them. Okay, hence why you learned how to add two different ugly expressions at one point in time. Why you learned how to do rational expressions. Because those were functions. I have a function here, a function here. It was all coming to this climax right here. Of what can we do with functions? Well, we can do all these things. So when you see f plus g of x, it's actually just saying, I have this function here, and I have this function here, and I'm going to add them together. I'm going to do the same thing when I subtract them. I'm going to do the same thing when I multiply them. I'm going to do the same thing when I divide them. Okay? Now, the biggest thing to remember is this, and I have it highlighted like crazy. I'm going to highlight it like crazy now, is remember this part right down here. All of that. The domain is the intersection. Okay? Remember the implied domain? Where you had all these functions going together, but then if one of them had a restriction, that's where you had to be careful. You're like, oh, it's all real numbers. Okay? Because of that guy right there. I have a restriction with that guy. Okay, sometimes it's gonna be all real numbers. Okay, so you have to play with it a little bit. Once again, Desmos helps out a lot, okay? But you don't have Desmos on your midterm and your final, so just be warned about that. Let me show you an example, very simple example. Given these two functions, f of x is equal to 4x squared minus 1 and g of x is equal to square root of x, find f plus g of x and find f times g of x. Well, guess what? F plus is easy. Because don't I just take it this way? I'm going to take this f of x and go 4x squared minus 1. And then I'm going to do what? Add what? The next function, right? I'm done. That's all I can do. You literally just took those functions and combined them together with a plus symbol. If I was subtracting, should you be careful about subtraction? Because what happens when you subtract? You might end up having to divide in or multiply in a negative, right? Sometimes you can combine like terms. You gotta watch out for that. You still might have to simplify a little bit. Now, where this one gets a little bit weird for you might be, one, if you start getting it wrong, is the multiplication. Okay? Well, let's look at this. When I have f of g, I'm going to see this. I'm going to see the square root of x times 4x squared minus 1. Well, you're going to get a big red bar if you try to put that in. Because now, technically speaking, you can distribute this guy, right? But it's going to be math. Okay, it's going to look ugly. Mathematically, is it wrong? No, but it's not what they want. Let me show you what you can actually do. Realize that what you're seeing with that square root of x, you're actually seeing x to the what? 1/2, remember? And then over here, you're seeing 4x squared minus 1. And now I have something I can multiply, right? Because now I can turn this into, hey, how about 4x 2/1 plus 1/2, because same base, add the powers, right? Minus x to the 1/2. This over here is going to turn into 4/2, obviously, because we're just going to add fractions there. And so my final answer here is going to be 4x to the 5/2 minus x to the 1/2. And if you wanted to, you could turn that back into the radicals that you want, if you want. If not, keep it as rational exponents. But kind of watch out for that. Like I said, the simplification part's going to be the part that gets you. Like you all understand that you can multiply this into here, but then that's why you learn how to do rational exponents. Okay? But notice the domain. What would be the domain? Well, I show you the domain. Whenever I show you this function, I'm going to show it to you right here. Well, notice those are my two functions. Here is my square root of x. Here is my what? My 4x squared minus 1. But notice it's the intersection, the red area. That would be my domain. Where do I get the domain from? Obviously, I get it from him because that's the guy with the restriction, isn't it? Okay, and what's the restriction? X can be what? Greater than or equal to 0, and since there's just an X in there. And so that's where I knew that the restriction, remember that implied domain that you learned back in like what? Chapter 3, somewhat in there? Okay, that's where you're getting the domain from. I'm going to finish this here, not here. I'm going to do one more thing, and I'm going to show you one example, and then we're done. This is where people are going to get like annoyed because it is a little tough. Okay, we don't do a lot of it, but you need to learn how to see it. Okay, composing functions. Let f and g be two functions. The composition of f and g denoted f with that little bitty weird circle, g, is the function defined by, and it gives you that little symbol there that is not multiplication, okay? We're composing this function where f is now also holding g of x inside of itself. The domain of f and g consists of all x in the domain of g for which g of x is in turn the domain of f. The function f of g is read f composed of g or f of g. This is what it actually looks like right here. You take an x, you plug it into g, you solve. Once you have that solved, you plug that g into f and solve again. I know you're like, what? What did you do? Okay. Let me go with the definition. Let me finish up a definition here. Important. F of g is not equal to g of f. Okay? They do not work backwards and forwards. Okay? You will see that. So put simply, you calculate your g of x. You're going to get a number, right? Like if I just gave you g of x and said, hey, if g is 2, couldn't you just plug that into that function and solve, right? And when you solve it, you're going to get a number. That number you now are going to plug in for f and solve again. Okay, let me show you, and then we'll be done for today. Notice I have two functions. F of x is equal to x squared, and g of x is equal to x minus 3. So find the following. F of g when it's 6. Since the g is happening second, I have to do g first. Okay, since it's saying f of g. Okay, so what we're seeing is this is f of g of 6. Well, what's g of 6? Well, isn't g of 6 is equal to 6 minus 3, and that's equal to 3? Right? Look right here. Here's the g of x. I just plug in a 6 there, right? Because it's telling me, hey, plug in a 6. So 6 minus 3 is 3. Well, now I take that 3 that I have solved for and plug it into f. Well, f is what? Because this is now going to turn into f of 3. And that becomes 3 squared, which is going to end up being what? 9. There's your answer. Notice you can do it backwards. How about g of f? Well, for g of f, which one am I going to calculate first? F, because it's g of f. Notice you're seeing this. G of f of 6. Well, f of 6 is what? Yeah, no, not 12. 6 squared. 36. Right. So that becomes a 36. So you've solved that f. So this now becomes g of 36. What's g of 36? It's 36 minus 3, which is 33. Notice these two are not equal. They don't work backwards and forwards. Does that make more sense how they work now? It gets a little bit messier, okay, but not horrible, especially whenever you're actually having to like compose them yourself, which you will do in your homework. You're going to come in there, they're going to give you two functions. They're going to say, hey, take this function and put it into this function. And literally all you're doing is this. You have f of x, you have g of x. If you see something of f of x, like say f of g of x, okay? You can put these functions together. Believe it or not, if you had to see this function together, you would see a function that looks like this. X minus 3 squared, okay? That's it. Notice the g of x is sitting here, right? What's on the outside of it? The squared. I have taken that function and composed it into the new function. Why do we do that? Because sometimes we want to be able to decompose them. We want to be able to pull them apart and go, what am I seeing here? Look at all these other functions that are happening. Okay, maybe I can pull these apart and look at them and see what's happening separate. Okay, we're going to go over this one a lot tomorrow. Okay, I'll download the notes today so you can kind of take a look at them. Because I do want to make sure we have enough time to go through all of the examples for this one. Okay, which we would have been able to go through though. The domain is pretty much the harder part, and there is a weird one. Let me kind of show it to you. That I'm gonna have to teach you tomorrow. This one right here, it's the very first one. Notice it's using that greatest common integer. Okay, you haven't really dealt with that, and you won't. Except for this question. So I've got to kind of just teach you real quick, which isn't horrible, but look what you have to do with it here. You're dividing with it. Well, its domain, when I show you, I want you to, because they don't really explain it in Hops about how they came up with the domain. And if you don't understand what the greatest common, they also call it a floor function. Okay, it basically says this: any number, you have to go to its closest integer, but you can't equal that integer. So like if I gave you like 1.9, it would be a 1. Because the nearest integer would be a 1. I can't go to 2. You can't go to the next one. You have to go to the nearest one that you're less than. Okay. It's weird. And so you have to think of all the little less thans. It's once it clicks, you're like, oh, I got it. It's the clicking. Okay. Or learn it well enough to get past your Hawks and it won't be on your midterm. Okay. So, all right. See you tomorrow.